So let me present myself. So I am Damien Delvaux from the Royal Museum for Central Africa. So in Tervuren, near Brussels in Belgium. So I spent quite a lot of time in studying the rifts. So the Baikal Rift in Siberia and the East African Rift, mainly the western branch. So in Africa. So I started in Tanzania, DRC, and this is a presentation on the Kivu Rift, so the central part of the Western Rift branch. So if you remember, so the rift has two branches, so an eastern and a western branch. So the western, which is here, is turning around the Congo Craton. And at the central part here, we have a topographic high with the Kivu Rift in the middle. And so on this screen, this figure shows the GPS velocity from Zaria et al. And we show that in the Kivu Rift, we have currently about between around 2 millimeters per year of divergence from the Victoria Plate from the Nubian Plate. So this region, in fact, the host rock is namely the Mesoproterozoic belt. So we have the Karagwe-Onkole belt here and Kibaran belt here, and the Archean cratons here, then the Mesoproterozoic belt here. So this is the setting, and so we recognize a small lake here with the Rwanda, Burundi, Uganda, Tanzania, and DRC. So when I studied this, I started to study this region about 10 years ago. So there was a problem that there was no homogeneous geological map across the border. So we have pieces from different sides. And so the first task was to build this synthetic geological map, which shows the basement here, and then mainly the Mesoproterozoic rocks, sedimentary rocks and granite, and then Neoproterozoic and younger rocks. So there are also several types of faults here. In black are the pre-Cenozoic faults, so probably related to the Pan-African event, so at the end of the Precambrian. And then red and yellow faults are faults related to rifts that I will detail now. So the first stage, we have Neogen rift initiation from 12 to 2 million years old. Those are this fault system in yellow, so relatively straight and continuing after the Lake Kivu here, much more to the southwest. And this is more or less this kind of movement. So we have an echelon opening of the rift, and here we have a link through the Luama Valley towards the central part of Lake Tanganyika. And Lake Tanganyika was opening but not connected to the Kivu Rift at that time. And then more recently, during a quaternary rift evolution, so on the north we have the same faults which are active, and in the south they tend to become more north-south, and then connecting so the western side of the eastern side of Lake Kivu, its two half carbons, to the North Tanganyika basin through the Ruzizi depression. So now we have this kind of movement, so which is more straightforward than the previous one. So in terms for the seismic hazard assessment, we need a neotectonic map. So we compile the late Cenozoic faults related to opening of the rift. This is what I have shown. Definition of neotectonic shame and classification of the fault system. We made an inventory of the thermal springs as indicator for tectonic activity, and also the compilation of historical and instrumental seismicity. We went, of course, in the field with colleagues from the University of Bukavu. There was some training courses and master degrees working on that. And so this is, well, one of the results is the map of thermal springs and fossil travertine that we compiled from existing material, mainly so archive material, and we visited a few of them around the lake, but most of them are quite old data, more approximately located, but show that nice distribution along this old branch of the rifts, which is no more really active for the moment, but still a lot of thermal springs. And also in the region of Bunakiri here, another branch, which is structured by faults of probably early Precambrian ages, but which apparently are still active. And then some distribution in Rwanda and Burundi. So there are some earthquake focal mechanism with SH horizontal extension expressed here, mainly extensional faulting, but some of them strike-slip faulting. We will discuss later, but we can already see that we have east-west extension here across Lake Tanganyika, but extension is turning on this branch. We will come back to that. And the epicentral depth of these earthquakes, so it's relatively shallow, so mostly between 16 and 6 kilometer depth. A few of them deeper, which might be due to location errors. One interesting earthquake was the Katana earthquake in 2015. So just near the Lwiro Research Center, where we had a seismometer there, and so the signal was even saturated, but we had other seismometer in the surrounding, and so there is a nice focal mechanism, of course not normal faulting, and which is compatible with some expression of faults that we can see from the landscape. We have thermal springs at the proximity, and also SLEs of early quaternary volcanic cones with volcanic basalt from about 1 million years ago. So this area is quite active. Here are the focal mechanism. This is a stress inversion of a focal mechanism, and you can see the main direction of extension, or more or less east-west in Lake Edouard, and turning progressively here to the Kauzi-Lila area. So this zone here, nearly now south extension, and east-west extension continue to Lake north of Lake Tanganyika. So we have a complex rapid change in stress fields if we move outside the main rift, the active rift, the central part of the rift. So for the seismic hazard, we compiled an homogeneous seismic catalog, about 1,000 seisms, and in fact we have 4 periods of recording. So this is pre-instrumental. We have so information from meteo stations where they recorded the felt shocks. So from that we could deduce some information, and then we have a second catalog here. We have a local local network between 55 and 65, and then after that there was less information, and then again a better catalog since 1990. So for the seismic hazard assessment, we only choose what is in this red rectangle here, and extracted this to get a more or less homogeneous catalog for a period of about 50 years. So this is the total instrumental and historical seismicity. So all the information with the different catalogs, the points in color in function of the different catalog. So we can see that we have a well distribution, of course, on the rifts, active rift here, on the fossil rift here, and outside the rift also. So this is after filtering for dependent events. So we have only independent events here, and we perform the seismic zoning in 7 zones, so in function of the geodynamic setting of the area. So we choose the northern part here, which is of the rift, which is essentially the magmatic part in which we have quaternary and active volcanism. We have the southern part of the Lake Kivu with Bukavu, in which we have no more volcanic activity. And then we have the link with North Tanganyika, the old prolongation of the rift here and outside the rifts. So we compute the Gutenberg Richter parameters using the maximum likelihood procedures, and the value reflect the lateral variation of the geological and tectonic context. In terms of maximum magnitude, so observed here versus the one obtained from the maximum likelihood. So for the non-magmatic rift segment, so south of Lake Kivu and Ruzizi, Tanganyika, we have 6.2 to 6.7 magnitude. For the Virunga Rutshuru volcanic provinces, this is 5.4, 5.45. So this is the lowest, in fact, we have. And then outside the rift zone, we still have 5.5, 6.15. So we see, in function of the geodynamic setting, we see some differences. Co-calculation of seismic hazard. So we use the Gutenberg and Richter parameter for the 7 zones. We use the Mavunga attenuation law of Mavunga 2007, the Crisis 2012 computer program with an average epicenter depth of 10 to 10 kilometers, and the results are expressed in peak ground acceleration in terms of G for a recurrence period of 475 million years. And so here are the results. So not surprisingly, we have Lake Kivu and Ruzizi region, Lake Tanganyika, with the highest hazard, above 4.25 for peak ground acceleration. And then we have the Virunga here with the volcanic region. And then outside the zone, we still have some hazard. So the smallest hazard is east, so in Rwanda. And here is some examples. So one, this one is here. Zone 2 is in Masisi, Walikale, and then we have here near Kamituga, the Fay branch. Ferris branch. Then we have the northern part here, and then finally the highest is here. So this is quite consistent with the idea that we have. I think this is this is the final slide. So the homogeneous geological results homogeneous geological map from the entire region. We have drawn neotectonic map and rift structure, a seismotectonic map. Sorry, historic and instrumental seismic catalog, and the seismic zoning in function of the tectonic context, and the seismic hazard. So we have an acceleration nearly 2 times stronger than previous models, and so this is explained as we need a detailed revision of the geology of the region. Coming back to here, what I wanted to say is that so the amagmatic region in which where we have the strongest magnitude earthquake is also, of course, of the highest highest hazard, and in contrast, the part of the rift in which we have volcanism has a more moderate hazard. So in terms of seismic hazard, we should expect most problems around Kivu and Bujumbura, while for Goma, as you certainly know, the main problem is the volcanic eruptions, but less the seismic hazard. Thank you very much.
Thanks, Damien. Are there any questions from the audience? If you want to either type in the chat or just raise your hand or speak. Okay, there's a question in the chat from Sasha.
So all the story is explained in this paper, which was published in 2017. So since then, of course, more seismic events occurs, and so there will be need after 10 years, I think, a new calculation with maybe more modern models to update these results.
Okay, thanks, Damien. Was that in response to Jacques Devachet's question?
Yes. Okay.
Good. You had a question specifically on that topic, so that answers that about the most recent catalog available. Also, there's a question from Sasha. Why do you consider the Western Rift segment failed if they host earthquakes and thermal springs? And also, do you use any GPS data, GNSS data, GPS data, I guess?
You mean this part in the southwest?
I'm not sure. It was from Sasha. He typed it in the chat. I guess so.
In fact, we do not, in terms of GPS, so we do not have, unfortunately, GPS data here from one side to the rift to the other one. So there are some GPS, but which were installed to monitor the volcanic hazard around the Virunga. So we cannot confirm the model of extension across the rift by Saria et al., which is also a model which is calibrated on data outside from this area.
Okay, thanks. I have a question about the earthquake error bars. Like, what are the error bars and the earthquake locations, and how do you deal with that in the seismic hazard assessment?
No, we did not deal with that in the seismic hazard assessment, but of course it's a few kilometers. So the data here are coming. So there are some data from the local catalog and from the international catalog, also the ISC. And so I think at this scale, you see 1 degree is 100 kilometers. So at the scale of the map, I think it doesn't make too much difference.
Okay, thanks. There's also a question in the chat about the accessibility of the data and results.
So the data have been published together as so the data file is as a supplementary material on the together with the paper.